Hi, my name is Ulf Petersen, and I'm a physicist at Roskilde University. And recently, OpenAI, they released their o1-preview model and made it available for us. And I thought this was really, really exciting. So one of the perks about this new model is that it can do reasoning. So it's not just doing one shot and trying and reflect of what it's doing, and it should be really good at problem solving. Also in physics. So what I wanted to do was not just give this a textbooks problem. I wanted to give it an unformalized physics problems. And these are problems that in my teaching I also see are really hard for the students because you don't know if you have to use classical mechanics or thermodynamics to answer them. And they are typically formulated in an everyday language, and you have to, as a student, figure out what assumptions are good, what kind of physics can I use to answer this question. And in particular, I wanted to take a question from one of the courses at Roskilde University. So we have a course called Problem Solving in Physics, which is exactly about these kinds of questions. A colleague of mine, Jens Højgaard Jensen, he's been designing this course, and he's been for a few years thinking about these kinds of problems. And so we have this Danish magazine Kvant, where he's in the back, in the last pages, he poses a new problem that the Danish physicists then they try to solve, and then he gives some solutions in the next issue, and with some didactical comments and generalization, how this is a general problem and things like that. So in spite of that, I wanted to try and give the o1 model some of these unformalized physics questions. And so now I have one in mind from a previous exam that I think would be good at this, about the energy consumption of a fan, that I also looked at in my last video. But here I want to look a little more into detail about it. So let me find this exam question. So here I found the problem from the exam. And it's in Danish, but I'll take it from here. And also Jens, he also gave a solution here that we can then compare to, and a method of how to solve it. And here we have the o1 model. And now I will copy in. I've prepared a prompt. So it says, you are an experiments physicist giving answers to the level of a first-year student. You are giving an unformalized physics problem in the form of an open-ended question. And then I start to explain this about how a physicist think. And here in the end, I'm then posing the question, how does the power consumption of a fan depend on its diameter and frequency of rotation? So in this question, it is about looking at a fan, and so you have different size fans, and they're going to have a different power consumption. And you can imagine if you make it larger, it should be a higher power consumption, and also if it rotates faster, it should consume more power. But how much more power? And that's what this question is about. So let's go back and see what how this o1 model is doing. And here it starts to think. And we can look at, oh yes, okay, so it's doing a lot of things. And it's giving a little summary of its thinking process here. Looking at clarifying things, transforming the problem, converting an open-ended question into a formal problem. So this is one of the hard things for the student that it's thinking about now. So here I think it ended, and let's close down this thinking. It took 30 seconds only. So let's read out what it found out. Determining how the power consumption P of a fan depends on its diameter D and rotational frequency F, or the angular velocity omega, using fundamental principles of physics. So that's how that it's formulating. Actually, this is a little more formalized than what I've done. So here it starts to look at airflow kinetic energy. The kinetic energy of a small mass dm moving at a velocity v is, so this is essentially the kinetic energy of the fan. And so it's converting this here into a power. I really like this because I think this is something that the students, they would know. They know this kinetic energy formula. And they would also understand this, I think, putting it into a power. Then it's considering this, the mass float rate. And so here is the dot here is the rate. And so here there's something with the density of the air, I assume. Yeah, and the cross-section area of the fan of the air moving. And then that's the velocity of the air coming through here. And then it's substituting the mass flow rate into the power equation. Nice. So that's plugging in what it had before here. And here it's getting something to the velocity to the third power. Then I'm guessing, yeah, here it's writing here that it's area and then velocity to the third power. Now it's gonna, for this area, we're gonna put in something with diameter, and so that's something with diameter squared. It makes reasons. And here, okay, this is interesting. Then it says here the tip speed, V tip of the fan is this. Yeah. It says here relating air velocity to rotational speed. So this is not a trivial thing. Assuming that the air velocity is proportional to the tip speed. I think that's a reasonable assumption, as it also says here for fans. In this equation, it's important to notice that there's some unknown factor coming in here. So then it says that the velocity that we had in the previous equation is proportional to this rotational frequency. And now we can substitute in this A and the V into the power equation, and we end up that the power is proportional to the diameter of the fan to the fifth power and the angular frequency to the third power. And you can also plug in the angular, the frequency that we were actually asked about. And so then it comes to the conclusion with this, that the power is proportional to this. And this is exactly what I asked for. So this question was about realizing this fifth power and third power here. Real world perspectives. That's interesting. I asked it in the end of the prompt also to put some perspectives on this equation. Energy efficiency. Larger fan operates at lower speeds. Operating at lower speeds can move the same amount of air as smaller fans at higher speed, but consume less power. I think that's really nice that that's come out of this equation. And then there's some economic impacts also. I think that is probably related a little to the first one. Then it's also discussing the assumptions that it made about the air density being constant. This linear relationship between air velocity and tip speed, I think that's a really interesting perspective. And then there's also something about neglecting laws, all the mechanical laws, which I think is also a really good point. Really nice. So let's read the final notes here. While the derived relation provides a fundamental understanding, actual power consumption will be affected by factors such as fan design, motor efficiency, and environmental conditions. Nonetheless, the d to the fifth, f to the third dependency highlights the significant impact of changing in diameter and rotational frequency in the power requirements. I think that's a nice conclusion. Okay, so it gave a really nice answer, and it did it a little bit different from what I had hoped it had done. So I had hoped that it would give something similar to what Jensi had in his answer. This answer here was a little bit overcomplicated. It would be more simple to use a dimensional analysis to answer this question. But it was not wrong. It was just a little better than expected, you could even say, if you wanted. But so I just want to show you Jens's answer, and we can just confirm that these exponents are the same. So here we have Jens's answer to the question, and you can see, so he's starting by writing up this equation 1 over here, considering what could be important for this problem, something with the density, this diameter, and in principle also the viscosity of air. So there's two ways that you can put energy into air. One of them is this kinetic energy, accelerating the air, and the other one is from friction that is then going to be putting the energy into heat into the air, and that has to do with the viscosity. So if you have a high viscous media, then you have a lot of conversion into to heat. For the fan, we are in a regime where all the energy is dissipated into moving the air molecule. If you have laminar flow, where things are flowing more lamellar, then you have that this viscosity is important. But here you have turbulent flow, and it's really the density that is important. So Jens is discussing that in his answer here. So let's see if we can find this power, his final answer. And so here we have Jens's final answer. So we have the diameter to the fifth and this frequency to the third power. So the same thing. And so Jens is solving this with dimensional analysis, which you can see, which is a simpler way of solving it that you can see down here. It's in Danish, but maybe you can get something out of it. I don't know. In conclusion, I think this was a really nice show of what this O1 model can do. It gave the right answer and gave some really nice perspectives on the equation also, and then really, I think, a pedagogical deviation of the equation, even though it was a little bit different from what Jens's solution was with this dimensional analysis. Maybe if you worked a little more with the prompt, you could also get it to show something similar to what Jens did. And you could even suggest, are there other ways of solving this? Maybe we could prompt it in another way and get another solution. So this video here is a follow-up to the last video that I did, where I received a lot of comments, and there was a lot of interesting discussions in the comments. And so I learned a lot from it. And so this was really important for me to make this video with all these comments. I will also put some information in the description, like links to this exam course here. Okay, thank you for watching.